with thanking the organizers for their heroic effort to put this great conference together in this fantastic place. Thank you. As much as we're all excited about the beautiful physics behind the fields of metamaterials and plasmonics, I guess we should admit very few applications came out of these fields. So, and the greatest challenge, in my opinion, is related to the necessity of developing new material platform so that materials would satisfy all the required criteria and, importantly, be compatible with the existing semiconductor industry where hundreds and hundred billions have been already invested. So in that regard, I think it's very important to look at materials which would bring applications to real life, applications related to the field of metamaterials and plasmonics. So, and of course, this is here of light, and we know that optical technologies actually have been changing the world. Just to remind you about the optical communication, optical fibers, our life would be different if not these technologies. When optical technologies are combined with new materials, with advanced materials, then they really could have quite a huge impact, which would change our everyday life. And that's actually what I'd like to bring up today. Let's say look at materials which could really make all the applications we are talking about real. And to further emphasize the point, the importance of materials, let me remind you that several recent Nobel Prizes in the field of photonics, optics, and electronics, one way or another, were related to materials and material developments. Well, to mention the most recent one, it's Nobel Prize in Physics for blue LED. It's all, of course, indeed related to material development. The graphene work in 2010, and of course, 2009 Nobel Prize for developing materials for optical fibers, which, as I already mentioned, change optical technology dramatically. So in this presentation, I'd like to discuss the challenges we have with the existing materials and what kind of new plasmonic materials could be considered and what we could expect by using them. And I will specifically spend more time on discussing so-called plasmonic ceramics or transition metals, such as titanium nitride. And I mentioned some application in the area of biomedical applications, energy conversion, data storage, and nanophotonics. Yet another thing, we should look into the future, and I believe, as many others do, that the next technology evolution is going to be quantum. Could metamaterials and plasmonic be part of that new technology evolution? And in that regard, I mentioned some applications of metamaterials, specifically their ability to control single photon generation, although there are many others which we are now investigating. And in the end, I discussed metasurfaces, which basically 2D version of metamaterials, which have, I would say, immediate applications. And in that regard, they're really changing the field, because applications in the area of flat optical elements are quite obvious, and they're already coming into industry. All right, let me start with this refractory plasmonics. Refractory in the language of metamaterial scientists means materials that can sustain high temperature. And I'd like to emphasize that it's a really important thing, because the whole idea behind plasmonics is to confine light down to nanoscale. But that's basically the only thing why we are so much interested in plasmonics, because with plasmonic materials, we bring light down to nanoscale, which implies that we always have very high energy densities, and as a result, elevated temperatures. And the traditionally used plasmonic materials, such as silver and gold, are very soft materials. When they are nanostructured, they cannot sustain even 400 Celsius. They start to change their form. There is a creep phenomenon. There is diffusion, and that's very critical. So we need plasmonic ceramics, material that can sustain elevated temperature. Without that, we simply really cannot talk seriously about devices. So basically, although this is the pyramid where we contributed, I mean, as a community, to all these three different directions, we discussed quite a bit these beautiful devices related to materials, ranging from hyperlens to negative refraction, of course, one of the most attractive thing about metamaterials that you basically could design and engineer optical properties by changing the shape and the sizes. But what I'd like to talk today about is the constituent materials, because it's really important out of which you build your metamaterials, because I think that's the area where we have most of our efforts to be concentrated. And this is, in my opinion, in my very biased opinion, indeed, a very important paper which showed the roadmap in developing materials that Harriet Water and Alexandra Baltaseva published already, 4 years ago. And they pointed out that indeed, depending on spectral range and particular applications, we are not limited to silver and gold only. There are a family of different materials to be explored, like in the mid-infrared, for example, perovskites, in the near-infrared, so-called transparent conducting oxides. And when you go to the visible, that's transition metal. Transition metals actually could make a difference and have superior properties, plasmonic properties. So holistically, you could think of two different approaches, because one could argue that one of the biggest problems, or at least one of the problems related to silver and gold, they are too metallic. The density of charge carriers, one could argue, is too high, meaning that the real part of the electric conductivity is negative. That's what makes them plasmonic materials. But it's too large when you go to the important telecommunication wavelengths. It's like -100. And when you build your metamaterial by combining plasmonic structure with the electrical semiconductor structure, you would like to have your effective permittivity quite often controllable and, let's say, close to zero. There are lots of applications related to epsilon near zero materials. And if you have the electric permittivity for your plasmonic components -100, whereas for the electric component, let's say +2, it indicates that the thickness of your plasmonic component should be like 50 times smaller, which is impractical. Because, I mean, if you're the electric component, let's say 10 nanometers, you cannot make something which would be just few angstroms. So it doesn't make sense. So it would be, for many applications, it actually would be better to have epsilon negative, but not that large in magnitude. Let's say comparable in magnitude to what we have with semiconductors. Let's say -2, -5. And another part of this, the imaginary part of the electric permittivity, which is responsible for losses, also proportional to the plasma frequency squared, which is proportional to the charge carrier concentration. So by reducing somewhat the charge density, concentration of charge carriers, so we would actually reduce losses, epsilon double pi. So in any way, we would like to control it, to change it, to tune, to switch. And you could move either from metals, making them less metallic by combining them with non-metallic constituents, or you could start with semiconductors and increase the charge carriers, making them plasmonic. So there are two ways actually to move in that direction. And we explore now both of these possibilities. So before I proceed, I'd like to show a couple slides which reflect my personal subjective opinion on where the plasmonics as a field is now. So, and what I think is going to come next. So this is a very well-known hype cycle, suggested first by Gartner. And basically, what it tells that if you have a new field, which normally starts with some technology trigger, with some discovery, one could argue in the case of metamaterials, it was this super lens. And then it goes to some, there is some exponential increase in terms of visibility, number of publications. It reaches a certain peak, but then people normally realize there are some problems with that technology, fundamental problems. And so there is quite a significant dip. But eventually, if you find solutions to those problems, and even though perhaps the final applications would not be as spectacular as expected in the beginning, you go through this disillusionment, go to this slope of enlightenment, and eventually, if the technologies succeed, you go to industrial applications, plateau of productivity. So in terms of plasmonics, that's the way I see this field. So one could argue that it started in 1857 by Michael Faraday, who first in a reproducible way started to make colloidal particles, gold and silver colloidal particles. That's, one could argue, is the beginning of the whole field of plasmonics. So then, of course, there are very important developments such as electron beam excitations of plasmons. First, we didn't have lasers. It was important to excite them. People used electron beams in the beginning. Source, surface-enhanced Raman scattering, indeed was very important, and particularly the fact that this dramatic enhancement, many orders of magnitude enhancement in Raman scattering, is related to high local fields associated with surface plasmons, as was pointed out by Martin Moskowitz. That indeed was very important. So extraordinary transmission, that's Thomas Edison and the company. So that's, of course, also drew lots of attention to the field. Metamaterials, with all this fantastic application ranging from superlens to clocking. And that's, of course, very sexy development, biomedical sensing, nanophotonic circuitry, spacer. But then we faced exactly that problem, materials. So, I mean, we were talking about these hundreds of beautiful applications, and show me them, where they are. So, and mainly the major reason why we don't have those applications is actually related to materials, which mainly were used to silver and gold, limited to silver and gold, and none of these materials is the most compatible. They have lots of problems. They are soft and expensive, so you cannot really tune their properties. So, but what we are now, I believe, it's this enlightenment period, because new materials are coming into the game, and that makes applications real. Now there is opportunity to bring those applications to real life. And in that regard, we should mention these 2D materials, graphene and others. That's indeed very important, because that makes by far more functional our plasmonic structures. These refractory plasmonics or ceramic plasmonics, which can sustain high temperature and can be compatible with semiconductor industry. And new applications are coming, including those related to quantum photonics, quantum science, which, as I mentioned, is really interesting development. Okay, so I think we actually in great enlightenment period, and I believe that good future is ahead. So let me start with these new materials we looked at, and the one we studied so far most is titanium nitride. It's indeed a very well-known material, which is used for many other applications. Ironically, for example, it's used in electronics, in chips, to prevent diffusion of copper, which is also common plasmonic material. But it never really was explored as plasmonic material itself. And as you will see in a moment, it's actually very good and plasmonic material, which in many regards better than gold, for example. So what we know about this material, it's hot and tough. It's used, for example, for these high-speed drill bits. There is well-established in processing. I mean, it's easy to make, and you didn't really have to create new way to produce this. It's well-known. So, and it is very refractory. So the melting point for titanium nitride is 3 times higher than for gold, for bulk. And which also indicates if you nanostructure titanium nitride, it would be able to sustain those elevated temperatures I was talking about. Most importantly, or at least very importantly, you could easily grow this material epitaxially. So you have single crystal quality in a very simple deposition by using, for example, magnetron sputtering. And you know that to have single crystal quality for gold and silver, it's absolutely heroic effort. I mean, it's extremely hard. Normally you have these island formations, which, and you have this polycrystal structure. So it is CMOS compatible, as I pointed out. It's used as a barrier, as a spacer, barrier layer actually, and so it's already in a CMOS line. And it's biocompatible. You know that it's used in dentistry. It's used for example, for implants. So in all regards, it's a really wonderful material. So here, by the way, you could see that indeed you could grow it epitaxially. That's the titanium nitride we grow, and it has this single crystal quality. So this is so-called non-stoichiometric material, meaning that you actually could design its properties. If you start with stoichiometrical point, when you have 50-50% for titanium and for nitride, when you slightly move from that point, by introducing some defects or vacancies, you actually dramatically change the charge carrier concentration, and as a result, the real part of the electric permittivity also changes dramatically. You could really tune it as opposed to gold. So it could be as negative as for gold, or it could be less negative by simply changing the conditions under which you actually make your material. Like these two particular titanium nitride, we obtain at 2 different temperatures, 400 Celsius and 800 Celsius. And they have very different real part of the electric permittivity. In terms of the imaginary part, I mean, it's still a lossy material, but what we obtain, it's actually a similar, very similar magnitude of the imaginary part of the electric permittivity as we have in gold. So when we look at these properties, to this ability to sustain high temperature, so we could place these plasmonic materials in this plot where I'm showing the wavelengths at which epsilon becomes negative. The real part becomes negative, meaning that your material becomes plasmonic. And here I'm showing the imaginary part, basically losses, and here the melting temperature. And if you look at silver and gold, the materials which are largely used for plasmonic applications, yes, they're indeed plasmonic in the visible, meaning that epsilon prime is negative, but the melting temperature is very low for bulk. And when you nanostructures, as I said, even 400 Celsius is a problem for these materials. And of course, tungsten is well-known refractory material, but it's not plasmonic really. So it has very poor, if any, plasmonic properties. And in contrast, materials I'm discussing now, transition metals or plasmonic ceramics, they actually have plasmonic properties, epsilon is negative, and very high melting temperature. So in terms of applications for these materials, let me mention just some of them, but they're all very important, and that indicates some particular applications which could be realized in the near future, actually right now. So in those in the biomedical applications, data storage, energy conversion, and nanophotonic circuitry. So let me start with these thermophotovoltaics. Of course, we know that with conventional photovoltaics, the biggest problem in terms of the efficiency is that if the energy of photons coming from the sun below the gap of your photovoltaic element, then those photons are wasted. They are not used really. And if the energy of photon is much higher than the gap, then the efficiency of conversion is not that high. So as a result, what you could buy now, it's something in the range of 20% with the theoretical limit around 30%. So, and it's also well known that if you do it in a different way, if you just heat your object up to high temperatures, let's say 1500 Celsius, then, and then you just let that black body radiate, and if you use frequency selective emitter so that it would let emit only the wavelengths which matches the gap of your photovoltaic cell, then the efficiency could be much higher. Theoretically, it could be 85%. It's the fact which is known for decades. The problem was the materials which would enable this type of conversion, energy conversion. And my point here that actually with these refractory plasmonics, you could do the job. And by the way, you don't have to use, it could be either we could use the sun as a source of heat to heat up your object up to very high temperature, or it could be just conventional thermophotovoltaics. It could be energy just as a heater. You could use gas, oil, whatever you want. So this is just to illustrate the point. So it's a very simple structure which we built. So it works as a perfect absorber when you use just these titanium nitride rectangular rings. It could be different structures. We just use this one. And so you could see that it absorbs the whole visible part of the spectrum coming from the sun. And the absorptivity is very close to 100% as needed. You could also make a very selective emitter. That is really important by using this rod-type structure. It basically acts like non-antenna, and it emits, in this particular case, it's designed so that it emits exactly the wavelengths close to the gap of gallium antimonide photovoltaic cell. So you could see that it's really close to the peak, and it should actually show very good performance. And to prove that indeed you could heat it up to the needed temperatures. So by the way, the whole structure could be just 100 nanometer in thickness. It's much simpler than what you could use, for example, with photonic crystals, yet another alternative approaches. So if you make these rings, for example, out of gold, when you heat up to 800 Celsius, you see what happens. Basically, it loses its structure. And with titanium nitride, the whole structure is protected. So we now heat it up already up to 1100 Celsius, and it still works very nicely. Well, since I mentioned these thermal sources, let me also mention yet another opportunity which you could use with these new materials. You could structure titanium nitride, like in this case, basically make a grating to make a coherent source out of your thermal black body radiator. So normally we believe that black body is completely incoherent, right? So in the broadband radiation. However, if you structure it like it's shown here, in this particular case, we design it that because of the propagating waves, surface waves, it's highly directional emission. So which means that you have high spatial coherence. You see that the width of this in angular distribution is around 1 degree only. And also, it's very coherent in the time domain, because you could see how monochromatic it is. It actually radiates only around 3 micron. You could design it to radiate at any wavelengths, and of course, this mid-infrared 3.5 micron, it's very important for a variety of DoD applications, actually. So data storage, yet another important applications. It's already like for 15 years or 20 years, we have one and the same density on disks which we use. And many companies keep talking about increasing the density by factor of 10 to 16, and there is this so-called HAMR technology, heat-assisted magnetic recording, but the stumbling block again, materials. So let me remind you what the idea here. If you would like to have a denser storage, you would like to have smaller bit sizes of these magnetic elements for which you flip the magnetic moment. However, smaller bit sizes brings instability, so you need higher coercivity materials. But if you have higher coercivity materials, that would require a larger magnetic field, which makes it impractical. So what was suggested long ago is just locally heat up the certain area, your magnetic bit. So when you locally heat it, the coercivity drops. And then you could switch the magnetic moment with a low magnetic field as required, and when you pull it down, you just record that bit of information. It's well-known technology, but the way to realize it, you need a very small near-field transducer, basically non-antenna, to hit it only very locally. And so far people use gold, and we face this well-known problem that even 400, 450 Celsius, which basically you unavoidably have, would destroy these near-field transducers. So by using tougher materials such as transition metals or plasmonic ceramics, that problem I believe could be solved. So yet another interesting application, arguably one of very few applications already existing for plasmonics. It's related to biomedical applications, the direction which is pioneered and pursued by Naomi Hallas from Rice. So in this case, they use nanoshells, gold nanoshells, to, and the reason why they use these nanoshells, because if you take gold nanoparticle, we know that the resonance is around 540 nanometers. But the transparency, biological transparency window, it's actually between 800 to 1100. So, and to move that resonance to this required spectral range, they make these nanoshells with a dielectric core and gold coating. So when you do this, particles become large, like 110 nanometers, which is a problem because then such large particles not that easy to remove from your body, from liver and kidney, and it would be better to use smaller particles, but most importantly, it's very expensive. I mean, the gold is very expensive. In contrast, if you take titanium nitride colloidal particles, it absorbs exactly in the biological transparency window between 800 and 1100 as required. And it could locally heat as effectively as gold nanoshell does, and that's actually the mechanism how you destroy cancerous tissue. You just send these particles in cancerous tissue. There are many ways to do it, by using ligands and many other things. And so when you radiate it in the biological transparency window, you excite plasmon resonance, you heat it, and you destroy cancerous tissue. So can we make these particles? And the answer is yes. And that's an important thing here. I should mention this particular research was supported by Office of Navy Research. Mark Spector is here, thank you. And we find it's a very important development. So you just take simple titanium particles, which cost next to nothing, very cheap, and you could take them of any size, and you anneal them in the atmosphere of ammonia. So basically you replace oxygen with nitrogen. And you get these beautiful titanium nitride particles. You could see that they have single crystal quality as opposed to gold nanoshells, which are indeed polycrystal, as confirmed by this diffractogram. So very nice quality, and they're very cheap as opposed to gold. terms of nanophotonic applications, this is a paper which just appeared, actually, maybe not even yet appeared. So let me show you our very recent results. We use titanium nitride for interconnects and also discuss the possibility of making optical modulator out of this. So first of all, interconnect. So you could see here titanium nitride waveguide, and please see the beautiful single crystal quality. It's 10 nanometer thick, and we demonstrated propagation length 5.5 millimeters, which is at 1.5 micron telecommunication wavelength, which is very comparable to what we obtained with gold. In fact, if you replace this oil, which we use so far, with silicon nitride, then propagation length increases up to 13 millimeters, 1.3 centimeters. So it's a very nice interconnect. And we also checked this material in combination with aluminum doped zinc oxide. And the beauty of this material, that close to telecommunication wavelengths, it actually has epsilon close to 0. And Neda and Geda, our chair, actually contributed a lot in discussing the wonderful properties of this material, CNZ materials. So why it's important in the case of modulator? If you have your epsilon very close to 0, meaning that if you switch it slightly, you could switch it from dielectric to metal. So even small change results, small change in terms of in epsilon would result in dramatic change in modulation because you're close to 0. And we showed that optically we could change reflectance and transmittance 40 and 30% respectively, which is quite significant. In fact, it could be more than that, and we are working on that right now. So, and when you combine it with titanium nitride waveguide, so you could have this modulator which has really good properties. So you can change, in this case, the charge carrier density by roughly 10 to the 20 per cubic centimeter. It's quite significant change. The response time is extremely short, 90 femtosecond. So basically it means that it could work in the range of 10 to 100 terahertz, the speed. It's very fast modulator. So modulation depth is very respectable, 0.4 dB for micron, and insertion loss is very low. So that clearly there are also good nanophotonic applications for these plasmonic ceramics. All right, let me now switch gears and discuss a possibility to use metamaterials for quantum applications. And I'd like to emphasize here there are lots of activities to study quantum properties in plasmonic structures. So I respect those activities. They are indeed important. But the truth is, I mean, quantum effects in plasmonic materials, highly conducting materials, are very low. I mean, they're basically classical. So it's all these effects existing indeed, but very small, and they manifest themselves at distances like 1, 2 nanometers. Why don't we take instead really strongly quantum systems, which the whole quantum community is pursuing now, and see how metamaterials and plasmonics could actually enhance those properties. So that's where I see potential applications for metamaterials to enhance really good quantum properties of those systems which people in the quantum community study. So in one of those quantum systems, attractive quantum systems, it's actually nitrogen vacancy in diamond. So the reason why people are so much interested in this particular system, because it's photostable source. It operates at room temperature, which is very important for devices. And it's, of course, inexpensive, easy to make. It's broadband. And perhaps one of the most important things, even at room temperatures, it has very long spin coherence time, which could be used for qubit to record this quantum information in this spin degree of freedom, and it could actually stay there 100 microseconds. So you could do lots of operation, and you could also write and read it optically. That's very important. So, and what we did specifically, we use hyperbolic metamaterials with this beautiful idea suggested by my colleague Evgeny Narimanov and Zubin Jacob, that with hyperbolic metamaterials, you actually could significantly increase the photonic density of states. It's a beautiful, unorthodox idea which indicates a different approach to increase the efficiency of emission of single photons in this case, which is a very important ingredient for any quantum photonic systems. So I would not discuss it much. I'm pretty much sure there will be lots of talks on hyperbolic metamaterials here. but the idea that for conventional materials, if you draw either frequency surface in K space, if it's isotropic homogeneous material, you have this sphere. If it's anisotropic, you have a spheroid. And if in one of directions, epsilon is negative, so that effectively your metamaterial acts like metal conductor in one direction and dielectric in another direction, then you have this hyperbolic surface. It's open. It means that you have unlimited access to very large values of K. That enables applications like a hyperlens. But most importantly for this particular discussion, if you look at the photonic density of states by looking at the volume between two different either frequency surfaces, this frequency omega and omega plus delta omega, it's unlimited, so it diverges. So basically it means that you have very large photonic density of states, and it's not related to Purcell effect, conventional Purcell effect in cavities. When near resonance, you also have very large density of states, but that occurs for a single frequency. Here, no near resonance is involved. It means that you not necessarily have to have some large losses because it doesn't require any resonance. And as long as your material remains hyperbolic, meaning that it acts like a conductor in one direction and as an isolator in another direction, then you have this increased density of states, which instead of being limited by wavelengths, inverse wavelengths cube, in this case, the parameter which plays a role is actually the thickness of layer which you use to build your hyperbolic metamaterial. And I should mention, of course, there are many groups working in this direction. I'd like to mention our chair, Menon, Mikhail Noginov, Zhao Wei Liu, and many others. So what we did, we made hyperbolic metamaterials out of titanium nitride. And actually, from perspective of metamaterial scientists, this is a beautiful structure because they tried for decades to combine metals with semiconductors and grow superlattice. It's a very huge challenge because they typically have very different structural lattices. And we succeeded in doing so. You could see that we have the single crystal titanium nitride combined with the electric based on aluminum nitride. But we had to add a little bit of scandium to match the lattices, and as a result, we were able to obtain this one big superlattice consisting of 20 layers of plasmonic material, titanium nitride, 5 nanometer thick, and 20 layers, dielectric layers consisting of this aluminum scandium nitride. And this is just an overview of what we obtained. Indeed, because of this hyperbolic nature of this metamaterial, the density of states could be increased. The closer to material you are, the larger the enhancement. It could go up to 100. So we indeed observe this increased rate of spontaneous emission, and that's what's needed. You would like to get these single photons at higher rate. And so we get roughly like 500,000 counts per second, which is a very high actually rate of generation of single photon. And to prove that it's single photons, we measure this G2 correlation function, which does go way below 2.5, which is usually considered to be the requirement for a single photon source. So, and the last part I'd like to discuss is actually metasurfaces. And this is a very important development, in my opinion, because the whole field of metamaterials, 3D metamaterials, has a huge challenge. They're usually very hard to make, and as a result, not that many demonstrated applications. With metasurfaces, which is two-dimensional version, you could easily make these materials, and you could immediately obtain a family of new devices. I should credit early work by Iris Hassman, Nikolai Zholorev, but truly game changer was work by Federico Capace, who actually showed a really family of new devices based on these metasurfaces. So this is the idea coming back to Federico's original paper, and basically it's very simple. When we look at the conventional Snell's law, it's dictated by the photon momentum conservation. But if you introduce these antennas along the interface, which shift the phase because of coupling to light, and if the antennas are different, the shift of phase is different. So eventually you would get gradient of phase along the interface, and as a result you introduce the momentum, because gradient of phase means momentum in space. And that allows you to send a beam in any direction you want, depending on the gradient you introduce. That modifies the Snell's law. You have this gradient of phase in the right-hand side of this equations which describe the conventional Snell's law. And so I'm a little bit biased here. There are many groups working in this direction. Shang in Berkeley, of course, Federica Capassa, DP Tsai, Bojevolny. I overview here the things we accomplished in Purdue and in collaboration with other groups. This is, for example, Huygens surface, where we control coupling not only to the electrical field component, but also to the magnetic one. And by doing so, you could match the impedance and get rid of reflectance. So this is CD spectrometer. I think it's a very important device because it's very, you know that circular Dick-Ray's spectrometer is one which is really used for many applications, biomedical applications specifically. Usually bulky, time-consuming. In this case, we use optical spin Hall effect to separate left and right circularly polarized light. They go in different directions with respect to the normal, and different wavelengths go to different angles. And the whole size is like 100 nanometers. And you could use white light, flash lamp instead of laser. So I think that's really a good device. So you could make a lens out of dielectric. It doesn't have to be metal. We did it actually more than a year ago. You could make a color hologram. That's actually very important for applications. By making slits of different size, you could design filters which would filter red, blue, and green, and that would gives you colors. And by controlling the orientation of these slits, you actually control what people call the barrier phase. And that actually enables this phase hologram. You could make a cavity much smaller than the wavelengths because the way a cavity works, so after one round trip, you have to restore the phase front. And normally it takes a size comparable to the wavelengths, but if you shift the phase by using this antenna, it could be actually much smaller than that. So in terms of like more spectacular application, I would say this is the one which combines the displays, which could be integrated with glasses. And so it's expected to have these beautiful characteristics, which are listed here. And this company, Bicatron, actually works in that direction. And so we expect here very interesting developments. So let me finish up with one idea suggested by my brilliant student, Amr, so which basically brings gradient not only in space domain, but also in time domain. So, and that opens up really interesting possibilities. That's very new work. So most importantly, you could make optical isolators out of this. So which implies that if light goes like this and reflected in this direction, it not only changes the color, but if you send the light in opposite directions, it would go not in a different direction from the original one, and also would have a different color. So you have here non-reciprocal light. So what is the idea? So conventional Snell's law results from actually momentum conservation and energy conservation. And if you use these conventional metasurfaces by introducing gradient of phase along the interface, then of course you send the beam in different directions to conserve the momentum. However, it's still reciprocal. If you use time variant metasurface, when phase also varies in time, then actually you switch from one isofrequency surface to another one after reflecting from such a metasurface. And when you send in opposite direction, in this case, you actually would go in a different direction. So it's non-reciprocal light in this case you could obtain. So if you look at the Snell's law in this case, because frequency changes, K also changes. So when it incident in this angle, it would be reflected at this angle, but when you send it back, it would not go in the same direction. It would be, instead of plus delta K, would get delta K. So if you have two ports, 1 and 2, so you could send it from port 1 to port 2, but if you send it in the opposite direction, it would not go in the same direction. It would be redirected. Or you could do it in the frequency domain. So basically, if you have optical cavity formed by two metasurfaces which change in phase in opposite direction, so that if light goes from here, the shift of frequency is omega plus delta omega, and it's supported by this cavity, it would go out. But if you move from in the opposite direction, since this metasurface shift the phase in negative direction, so that which is not supported, the frequency omega minus delta omega is not supported by this cavity, it would not go out. This is non-reciprocal light. All right, let me sum up. So I think this new material platforms is really important, and there is very good progress in that direction, which opens these applications in data storage, nanophotonics, energy, and particularly interesting applications, I think, in the area of quantum, where I think we could really expect interesting results. So with this, let me just acknowledge contribution of students. We do this work in close collaboration with my colleague, Alexander Balta. So those students and postdocs which are involved in this particular research I discussed, and here are some relevant publications. Thank you very much.
Start with the question. Vlad, you mentioned that the titanium nitride is an example. One of its advantages is the fact that you can epitaxially grow that. And you showed very nicely with this hyperbolic structure that you have. How would you envision such layered structure, but with many different materials? Not necessarily a pair, but could be more than two. In other words, to have kind of like, multi-layered structure, each one of them, one atomic thing.
Right, well, having epitaxial layers is indeed very important, because in the end of the day, performance depends not only on material properties, but also on the quality of your material. We all know that the fact that, let's say, gold waveguide is not perfect, it's polycrystal, there is scattering on these grains out of which gold consists. As a result, even though epsilon double prime could be not as high as you would like to, overall performance is actually very good, because you don't have any grains. You have this beautiful structure. In terms of growing multi-layer structure epitaxially, it's a challenge, but we already showed one when we combine it with aluminum scandium nitride. The good news that titanium nitride could be grown epitaxially not only on magnesium oxide, which matches the lattice, but also on a number of different other materials, sapphire, silicon, because at the end of the day, it depends on the surface energy. If you control it, you could grow it epitaxially even on a substrate which has different lattice. And that's something we are working on, but we already grew this structure on a number of different substrates, including the sapphire and silicon, which is very important. The lattice match could be overcome in terms of substrate. If you would like to have multi-layer structure, that would be a bigger challenge. And I'm not in a position now to say whether it's possible. But what I do want to say that in the end of the day, to have the super lattice, you don't necessarily need matching of lattices. There are ways around of that, although it's a challenge to do. Okay, the question was why we choose titanium nitride over zirconium nitride. That's a very good question. In fact, zirconium nitride is more metallic than titanium nitride, meaning that epsilon prime is larger in magnitude. And actually, there is no much reason for that. We just started with titanium nitride. I should say that with zirconium nitride, epsilon double prime is larger than in titanium nitride. So, but we certainly should look, and we are looking at, and I encourage other groups to look at this zirconium nitride, as well as other hafnium nitride, tantalum nitride. All these transition metal nitrides are very, very promising. Basically, it's a brand new field. We just started with titanium nitride. I'm pretty much sure for some applications, zirconium nitride would be better than titanium nitride.
Now we're going to have our coffee break, and I was told that the coffee break is going to be in the cafeteria upstairs. That's right. So have a great coffee break, and the poster sessions there as well, and we'll reconvene at 11 o'clock. Thank you.